Students, here we are. All right, BC Calc students, it looked like I chopped off the top of my head there in the video. Okay, it's great to see you. We're just going to pick up where we left off here. So let's take a look at this. Here's where we were. We are trying to solve for the average value of this function here. And we just equated this area under the integral, the area under the curve, that's called the integral, equal to the area of this rectangle. And so I just want to solve for this. And so you guys, the obvious way to do it is to divide both sides by b minus a. And so I end up with the average value of the function is equal to the integral from a to b of f of x dx divided by that width b minus a. Okay, and that's lovely. Okay, and you can memorize it that way and you'll be fine. It's just doing all of this gets kind of messy, and then you're dividing by this. And so the way most textbooks will actually write this is they'll bring this out front as a fraction, 1 over b minus a, and then multiply that by the integral from a to b of f of x dx. And so this is the form that you'll see all the time, and that's the one you really should be familiar with, okay? The average value of the function is just the area of the function divided by the width, right? If you think of a rectangle and somebody tells you its area, and then they want to know, and they give you the width, and they say, well, how, what's the height or whatever, you would simply divide by the width to get the height, and that's exactly what this is telling us, okay? So as an example, you might be expected to do something like this. It says the graphs in problem 2 are in fact for this function. And so we're going to estimate here. It looks like the average value of this function, this goes 0, 1, 2, 3, 4, 5. So it looks like the average value of this function here is about what? 1, 2, 2.8 or 2.9, something like that. So let's see how this works, okay? So what is the average value of this? Well, the average value of this function is equal to 1 over b minus a, 2 pi minus pi over 2. And this is a good reason why it's perhaps best to pull this out front instead of having this underneath another messy thing here. That would be multiplied by the integral from pi over 2 to 2 pi of, well, what function was it? It was 3 plus the cosine of x. And then that's the height of each rectangle, but then you need to multiply by the width of each rectangle. Okay, this is infinitesimally small. This is telling us that x is going to take on every single value between here and here. There's an infinity of them, and we're going to add up an infinite number of infinitesimally small rectangles to give us the area of the thing. And so basically what's happening here is this is the area under the curve. That is this area here. And if we divide that by the width, we end up with the height of this rectangle over here. Okay, so now it's just a question of evaluating this. So what we need to do is think of a function. If f of x is equal to 3 plus the cosine of x, what we need to do is think of a function capital F of x. What would that be? So that by definition, f prime of x, the derivative of this function, equals 3 plus cosine of x. Okay, and this is usually where I like to call on a student in class, because it kind of puts you in a place where you need to think. The integral of this, the antiderivative of a constant, is just 3 times x. Okay, and the derivative of the sine is equal to the cosine. So I'll do like so. And then I want to have a constant c, because anytime you anti-differentiate, anytime you take the integral, you have to be concerned about an arbitrary constant c that might have been there. And so let's just be sure. If I take the derivative of this, do I really end up back where I started? That's key. This is what I was looking for. But let's just be sure. The derivative of this is 3. The derivative of the sine of x is the cosine of x. And then the derivative of a constant is 0. So sure enough, I ended up where I want it to be. So what the fundamental theorem of calculus tells us here is it says just evaluate this function at 2 pi and subtract this function at pi over 2. And so the average value of f is equal to 1 over, all right, you guys, let me think about this. I want to get a common denominator here. All or I suppose you could just think it through. If you have 2 of something and you subtract half of that thing, you have 1.5 of that thing, or 3/2 of it. But let me rewrite this as 4 pi over 2 minus pi over 2. So I'm dealing with my fractions there, and then that would be multiplied by, okay, what I have to do is evaluate this function, 3x plus the sine of x plus c. I need to evaluate it at pi over 2 and at 2 pi. You put this one in first, and then you subtract what you get when you put this one in here, okay? So let's clean this up. This would be 1 over 3 pi over 2, okay? And that's called a compound fraction. It's kind of messy. The way I handle these is I don't do the copy dot flip thing. I just multiply the top and bottom by 2. Okay, the denominator is 2. And so what that does for me is it gets this to go out, and you end up with 2 over 3 pi. And then I multiply that by, okay, plug in the 2 pi first, okay? So 3 times 2 pi is 6 pi plus the sine of 2 pi plus c. And then I have to subtract. Now I plug in a pi over 2. So put the 3 in there. 3 pi over 2 plus the sine of pi over 2 plus c, like so. Okay? All right, and so now, and this is the thing about using your calculator, you guys. There's a lot to evaluate there. The truth is, on your BC calculus test, if you were to get a question like this, I don't think they'd give you something this simple on the free response, but if they did, you could stop working right there. And as long as a competent algebra student could work out this answer, you're done. I want you, of course, in my class to carry it through, because I want you to learn to simplify your work. But on the actual test, if you leave an answer like this, you're fine. Actually, you could have left this like so, okay? Not this, but you could have left the denominator like this, messy, and not had to clean it up at all. And you know, the issue is, why lose calculus points for an algebra mistake, right? But I want you guys to get better at both, okay? So this would be 2 over 3 pi. Okay, and then we evaluate 6 pi plus, well, the sine of 2 pi, you guys think of the unit circle. The sine is the y coordinate on the unit circle. I'm sorry, 2 pi is here, right? I have to always do things in mirror image when I'm doing a video camera, and it's confusing. So here you are, the sine is 0. So that would be plus 0 plus c. Okay, and then I'm going to subtract 3 pi over 2. And then the sine of pi over 2, well, there's 0 and there's pi over 2. The sine would be 1. So it would be minus 1 minus c. Okay, and no matter how much room I leave on my paper, I always manage to need a tiny little bit more. Okay, so here we have 2 over 3 pi times 6 pi. I'm looking at my common denominator here. 6 pi. I'm going to write that as 12 pi over 2. Okay, plus 0 plus c. The c's are going to cancel out. So minus 3 pi over 2, and then minus 1, like so. Okay, and let's see what that would give me. This would be 2 over 3 pi times 9 pi over 2 minus 1 would be 2 over 2, like so. And so I'd end up with, oh, this is going to work out kind of nicely. 2 over 3 pi times 9 pi minus 2 over 2. These 2's go out, and I end up with this answer, 9 pi minus 2 over 3 pi. Okay, and heavens knows, I may have made a big mistake somewhere in there, and you guys will let me know. Okay, let's try this out. I was predicting a value. I was predicting a value of about, what, 2.9 or so. Okay, why am I not on the camera? About 2.9, right? Something 2.8, 2.9, something like that, okay? And let's check this out. So let's type it in. 9 pi minus 2 divided by 3 pi. You guys notice I put parentheses around there to make sure that it's dividing by 3 pi and not dividing by 3 and then multiplying the result by pi. And let's see what we have there. We get 2. So we use this decimal approximation, 2.78779. 3 decimal places would suggest you round here. That would be 2.788. 8. That's 7. If it's 5 or above, give it a shove. You would write this on your paper as the average value of that function. And sure enough, there it is. Let me check against my previous work that I already did. And there we are. There I have it. Okay, we are good. Okay. All righty. Okay, let's move on. Suppose that f and g are continuous functions and that we know some information, okay? So you guys, these are classic multiple choice type questions. Okay, this dot is like a bullet. It's not a multiply, okay? That's just the word processor format. We know these 3 facts, okay? There the 3 facts are, okay? Use the rules in table 5.3 to find each integral. If I integrate f of x from 3 to 2, I'm just changing the bounds of integration. And so they have that listed here. They call that the order of integration. So if you integrate from B to A, that's the opposite of if you integrate from A to B. And so that's the order of integration rule. And so this would simply be the opposite of -5, which would just be 5, like so. Okay. All right. What if I integrate from 2 to 2? Okay. Well, that one is covered here. That's called 0. If you integrate, if you stop and go at the same exact spot, I mean, think of your car. It's like saying, how far did your car travel between 0 seconds and 0 seconds? I mean, it doesn't matter what speed your car is going. You're not allowing the car to move at all, okay? And so the answer would simply be 0. You're not moving. There's no area under the curve if the thickness of the rectangles are all 0, right? So of the one rectangle is 0. So you end up with that simply being 0, okay? All right, this one, you're allowed to bring a constant out front whenever you're integrating, just like you can when you take the derivative, right? You just write down the constant and worry about the rest of everything. So they have that in here, a constant multiple. If you integrate a function being multiplied by a constant, you can pull that constant out front like so, okay? And so there it is. So this would be 4 times the integral from 2 to 3 of f of t dt. Now, this might concern you. This says t here, and this up here says x, okay? And you might think, well, I don't know. They didn't tell us that. But remember, this t is known as a dummy variable. I know that's kind of a demeaning thing to call it. I hope that variable doesn't have any feelings. This is the same thing. It's a dummy variable, okay? And what that means is it's just there as kind of a placeholder. We want to evaluate this function at every single value of x between here and here and multiply that by the width of each rectangle, which is infinitesimally small. We represent that as dx. And if we add up all of those rectangles, we get -5. Okay, somebody else comes along and does the exact same thing. They figure out that the height of every single rectangle, making t sweep from 2 to 3, and then they multiply all of those by the width of each of those, dt. It doesn't matter what variable it is. What matters is that these have to match. And if that's the case, that would be the same as this. Okay, as long as you're not changing one to x and one to y, that would be very different, okay? And they already gave us this in the given information. They already told us that was -5. So this would be 4 times -5 or -20, okay? All right, and then finally, part D, this has a combination of rules in here, okay? So this one says if you have a sum and difference of 2 functions, if you're integrating a sum of 2 functions, it's the sum of those 2 integrals. If you're integrating the difference of 2 functions, it's the difference of the 2 integrals, okay? And so what you're allowed to do here is basically just rewrite this as the integral from 2 to 7 of the first piece, f of x. And you guys, you can literally distribute the dx's there. You really can do that when you're doing this, dx. And then minus the integral from 2 to 7 of 3g of x dx. Like so, that's essentially what it, maybe I shouldn't call it the distributive property. Maybe I'm misspeaking. But I'm simply following this rule here. Okay, I'm going to add the integrals of each of these. Oh, yeah, no, I could absolutely add the integrals of those 2. I could absolutely do that. Okay, there'd be nothing wrong with that at all. I actually could integrate from a to b of f of x dx plus g of x dx. That's a little bit of a weird way of writing it, but that's perfectly okay. It says exactly the same thing as what we have going on here. Okay, and so Now, this one we already know. They already told us this. This one they already told us that that was equal to 20. Okay. And then this one, I have an issue here. I have this pesky 3 in front, which is a constant. And so then I have to use the constant rule here, which says, the constant multiple rule, which says, hey, take that constant out front. So you have the k in here, just put it out in front, like so. So let's do that. So then this would be minus 3 times the integral of 2 to 7 of g of x dx. And that, they have told us already, the integral from 2 to 7 of g of x dx is 4. So we have 20 minus 3 times 4 is 20 minus 12, or 8, like so. Okay. All right, last one. They have a couple of problems like this in the homework from time to time. Why must this integral from these random numbers 11 to 15, why must this be less than 10? Okay. And so the idea here, they want you to think of this in terms of its maximum value. Okay. So even though we know the cosine oscillates between -1 and +1 all the time, what they're saying is, well, why must this be less than 10? And this is the domination idea here. This is referring to this. It says, well, basically, if you have one function that's bigger than or equal to another function and you integrate that, it will be greater than the integral of this function here. So if one function's values are always greater than or equal to another function's values, and you integrate them, the dominant one will be bigger. The dominant integral would be bigger than the other integral. And so basically, what we can do is we can create a dominant function here where we say the dominant function would be go from 11 to 15 of, instead of cosine of x, let's just say it +1 times dx. And that's our dominant function. And since 1 is always greater than or equal to the cosine of x for all x, this function's integral must be greater than or equal to this function's integral, right? From 11 to 15 cosine of x dx. Okay. Well, what is this one's area? Well, if you integrate this, you would just have x plus c, and you would evaluate that from 11 to 15. I feel a little silly doing that because if you think about what this thing looks like on the x-axis, you go from 11 to 15, and this function is a constant function. It's always 1. We're asking what's the area of that rectangle? When we know that rectangle is 4, right? But you could go ahead and do that and plug in the 15, and you'd end up with 15 plus c minus 11 plus c, which is 15 minus 11, which equals 4. And so the biggest this integral could possibly ever be would be 4. So that's already less than 10. Okay. And so there's no way that that integral could ever possibly exceed 4. So it certainly has to be less than 10. Okay. So the integral must be less than or equal to 4, which is less than 10. Okay, so you'll get this type of question from time to time, and it's not trying. You won't have a calculator with you, and you might freak out and say, "Well, I need a calculator." You really don't. The idea is to think of a function that's always greater than or equal to the cosine. A very simple function, a constant function of 1, would do the trick, and evaluate that function's area. And if that function's area has to be bigger than this area. Okay, and so the biggest that could ever possibly be would be 4. And so that takes care of that problem there. Okay. All right, you guys, get on to the Google Doc homework portion where you do a little bit of reading and interpreting what these rules are saying, and then get on to the textbook homework. Okay, you guys. All right. Take care. All right. Bye.